Hello everyone, welcome to Das Lake. This is lecture number 1 of the 1000 question series of heat transfer, and the topic for today is conduction, and this is the part 1 of the conduction. Okay, so let's start the questions. This is question number 1. The temperature distribution in a concrete slab is given as T is equal to 3x square plus 3x plus 16. Okay, alpha is given. Alpha is thermal diffusivity, and we have to find out the rate of change. Okay, rate of change uh, of temperature with respect to time. Okay, there is a printing mistake here. So we basically need to find out del T by del tau. Okay, so what do we know? Okay, the heat diffusion equation. Okay, heat diffusion equation, okay, for uh, 1 second, constant k, okay, one dimensional, no heat generation. Okay, for one dimensional constant k, no heat generation condition, the heat diffusion equation will be del square T by del x square will be equal to 1 by alpha del T by delta. Okay, this is the heat diffusion equation given in this condition: constant k, one dimensional, no heat generation. Okay, so we need to find out this term. We need to find out this term, del T by del tau. Okay, del T by del tau, we need to find out this term. Okay, what do we have? We have T in terms of x. Okay, T is equal to 3x square. I think it is not visible to you. Let me change the color of the pen. Okay, T is equal to 3x square plus 3x plus 16. Okay, T is equal to 3x square plus 3x plus 16. If I'll differentiate it with respect to x, I will get 6x plus 3. Yes or no? Now if I will differentiate it again, then I will get 6. Yes or no? First differentiation is 6x plus 3, and the second differentiation will be 6. Here I have this term now, del square T by del x square. This is, yes or no? Yes. So if I'll put it here, that the value of this is 6 is equal to 1 by alpha is given in the question. Okay, 0.003, 0.003, and the thing that we want to find out is del T by delta. Yes or no? Yes. So keeping del T by delta in this side and giving this term to the left hand side, so it will be equal to, okay, del T by delta will be equal to 0.018. Any doubt? 6 into 3, 18, into 0.001, that will be 0.00018. Okay, this is our answer, option D. So let's move to the next question. Okay, here is the next question. Consider one dimensional steady state heat conduction across a wall. Okay, I will draw the figure of thickness 30 mm, thermal conductivity of 15 watt per meter Kelvin at x equal to 0. A constant heat flux Q double dash is equal to 1 into 10 to the power 5 watt per meter square is applied. On the other side of the wall, heat is removed from the wall by convection with a fluid at 25 degrees Celsius. Okay, and heat transfer coefficient is 250 watt per meter square Kelvin. The temperature at x equal to 0. Okay, so okay, we have a wall like this. Okay, let's suppose this is our wall, and here, okay, I'm not changing the color. Oh, okay, this point is our x is equal to 0. Okay, and the thickness, okay, the thickness is given as 30 mm. So uh, okay, this thickness is 30 mm. Okay, and there is a heat supply at x is equal to 0. Okay, there is a heat supply. So here there is a supply of heat. Okay, and we have the Q dash as 1 into 10 to the power 5. Okay, the thermal conductivity of the material is also given. So and on the other side of the wall, heat is removed by convection. Okay, uh, here it is removed by convection. Okay, and H is given. So to solve these type of questions, we first need to do the electrical analogy, and we need to draw the resistance diagram. Okay, so now I'll do the draw the resistance diagram for this. Okay, I'm drawing it here for your convenience. Okay, let us do here. Okay, I'm drawing the resistance diagram for this. Okay, so uh, here at this section before x is equal to 0, there is nothing is defined, so we'll start from x is equal to 0. Okay, this is our starting point, and this portion, okay, the first resistance that will come to us, that is this body. Okay, so this body will give us the first resistance. Okay, now another resistance will come here. This is the conductive resistance. Another resistance will come here. So this is our another resistance. Okay, so at this point the temperature will be TO, and at this point the temperature will be T infinity. Okay, so what is actually asked in the question? The temperature at x is equal to 0. Okay, so we have to find out this. Okay, I'll find out it. So let us write the value of this resistance, the first resistance. So that is L by Ka. Conductive resistance is L by Ka. So L is this length, that is 30 mm. So this is 0.00, sorry, 0.030, okay, L divided by K. So K is given in the question, that is 15 watt per meter Kelvin. Okay, so 15, okay, L by K A. Okay, now this resistance, the convective resistance, okay, it will be 1 by Ha. Convective resistance is 1 by Ha. 1 divided by H. What is H? H is given in the question. Transfer coefficient, that is 250 watt per meter square Kelvin. So it is 250, okay, into A. Okay, 250 into A. So let the heat that is flowing here, okay, let that is, let that be Q. So the heat that is flowing between temperature T naught to T infinity is Q. So what we can write the expression for Q? What can we write for Q? We can write Q is equal to, okay, this is not visible. Okay, let us write in this. So Q is equal, it is also not visible. Okay, it is okay. Let us write some deep. Q is equal to, okay, T naught minus T infinity. T infinity is given in the question, okay, that is 25 degrees Celsius. Okay, T infinity is 25 divided by R total. R total means, as this is in series, so R total will be R1 plus R2. So R1 is this 0.030 divided by 15 A, okay, plus 1 by 250 A. Okay, this is Q, and Q is equal to, okay, this heat flux. Okay, this is the heat flux, and Q is equal to heat flux into area. Okay, the heat flux is 10 to the power 5, so we can write it here is equal to, okay, is equal to 10 to the power 5 into area. Okay, now there is only one unknown that is here, that is T naught. T naught is the only one unknown, rest of the thing is there. So now we will solve for T naught. By solving T naught, that is very simple. Okay, A and A will be cancelled out. Okay, this A will be go to numerator, and numerator from here to here will be cancelled out. From here T naught will be 625 degree Celsius, and this is our T naught. Okay, T naught is the temperature of this portion. X is equal to 0, T is equal to 625 degrees Celsius. Okay, now let's move to the next question. Okay, this is our next question. Let's read it. Steady one-dimensional heat conduction takes place across the face 1 and 3 of a composite slab consisting of slabs A and B. in perfect contact as shown in figure. Ka, Kb denote the respective thermal conductivities using the data given in the figure, the interface temperature T2. Okay, we have to find out this temperature. Okay, so the figure is already given, so we just need to draw its uh, what the network diagram. Okay, so here the temperature is already given, that is T1. Okay, the temperature is already given, that is T1. So we'll start with T1. Okay, this is T1. The first resistance that we'll encounter will be this slab. Okay, this is the conductive resistance. Okay, so the first resistance will be by the conductive resistance of the slab A. Okay, this is the conductive resistance of slab A, and here the temperature, what I have said, it is T1. Okay, this is the conductive resistance of the slab A. Now I will reach at temperature 2. This is temperature 2. Now I will enter into the slab B. Now I will face the resistance from slab B. Okay, so this is the resistance offered by slab B. Okay, now finally I will end up at temperature T3. Okay, this is the temperature T3. So can I write the conductive resistance of slab A? Okay, that is L by Ka. So L by Ka. L is 0.1 meter for slab A. 0.1 L by K. K is given, that is 20. Okay, into A. Okay, now I will write the conductive resistance of slab B, that is also L by Ka, that is 0.3 divided by Ka. K is 100 into A. Okay, so the I will say one thing to you here. Okay, the heat that is traveling here. Okay, can I say, as this is in series, the heat that is traveling between T1 and T2 is also traveling between T2 and T3, the same heat? Yes, cause these are in series. Yes or no? As these are in series, the same heat that is traveling between T1 to T2, that is also traveling between T2 to T3, cause it is also in steady state. Yes or no? So what I can write, the QA, okay, the QA, okay, the heat in A, and QB, the heat that is traveling through B. QA will be equal to QB. Okay, what is QA? QA is T1 minus T2 divided by RA. T1 minus T2 divided by RA is equal to, what is QB? T2 minus T3 divided by RB. T2 minus T3 divided by RB. Yes or no? Yes. So T1 is 130 degree. It is given in the question. T3 is 30 degree. Okay. Now I will put them, 130 minus T2. Okay. Divided by RA. RA is 0.1 divided by 20. 0.1 divided by 20 A is equal to T2. I have to find out T3 30 degree, T2 minus 30 degree divided by RB. RB is 0.3 divided by 100. 0.3 divided by 100. Okay. In this expression, there is only one unknown, that is T2. Yes or no? Only T2, what we don't know. So T2 we can easily find out from here, and that will be equal to 67.5 degrees Celsius. Okay, I have missed an A here. Okay, it is there. So T2 is 67.5 degrees Celsius, and T2 is the temperature of this interface. 67.5 degrees Celsius. So now let's move to the next question. A plane slab of thickness L and thermal conductivity K is heated with a fluid on one side P and other side Q is maintained, okay, at a constant temperature TQ of 25 degree Celsius as shown in figure. The fluid is at 45 degree, okay, uh, and the surface heat transfer coefficient H is 10 watt per meter square Kelvin. The steady state temperature TP. Okay, it's very simple question. So again we have to do the same thing, the network diagram. First here the convective resistance, then here the conductive resistance. So first, okay, we'll start from T infinity. First a convective resistance, okay, there is a conductive resistance, okay, finally we will end at Q. Okay, this is our Q. Okay, this is our P, and this is T infinity is already given. This is T infinity. Okay, so T infinity is 45 degree. Okay, 45 degrees Celsius. Q is 25 degrees Celsius. We need to find out the TP. Okay, the first, okay, the convective resistance will be 1 divided by HA. H is 10 into A. Okay, the conductive resistance is always L by Ka, so it will be L that is 20 cm, that is 0.20 meter, divided by Ka. K is 2.5 A. Okay, the same thing that I have done in the last question. Okay, but I will do it again. Okay, let's suppose this is, as this is in series, let's suppose this is Q. Okay, this is not at all visible. This is, let's suppose that is QA and this is QB. Okay, or you can say QH and QC. QH is the convective heat transfer that has been taken place from the fluid to the body solid, and the QC is the conductive heat transfer that is taken place from the end P to the end Q in the body. Okay, so as this is in steady state, so QH is equal to QC, because both of them are in series. Okay, so QH is T infinity minus TP divided by RH, and QC will be TP minus TQ. Okay, TQ divided by RC. Yes or no? Hope you have understood this. T infinity is given, that is 45. Okay, TP we need to find out. RH is 1 by 10A. Okay, is equal to TP. We need to find out TQ 25. RC, this one 0.20 divided by 22.5A. Again, in this expression there is only one constant, right? The A and A will be cancelled out. You may think that I am cancelling. How can I cancel them? Actually, they will go to the numerator. Okay, this will go here, and from here they will be cancelled out. Okay, so again, very simple. We need to find out just TP, because there is only one unknown, and TP. Okay, TP is equal to 33.88 degrees Celsius. Okay, this is our TP. So this is all for today. Hope you have enjoyed the uh, class and questions. So if you liked it, then hit the like button, and if you want such videos, then do subscribe. And one more thing, sharing is caring. So if you find it helpful, then share it among your friends. Thank you. We'll meet in the next video. Goodbye.